Super pleased to have Professor Jeltima with us. She's a professor at UC Santa Cruz. I think Associate Director of SCIP, maybe?
Yep.
That's right. That's the Santa Cruz Institute for Particle Physics. She's interested in dark energy and heavily involved in all the dark energy missions and also the Rubin telescope, that's a time series telescope that we probably heard of before. Most of you heard of it. It's should start up some kind of operation next year. Maybe the year after. You can correct me on.
Yeah, I think there will be some form of first light in a yearish. It depends. The shipping of the camera has been somewhat delayed, and it's not clear how delayed, but you know, so there's now big time windows. But I think, you know, at least with the commissioning camera, about a year from now, we'll get some data, and I don't think it's maybe a couple months delay. It's not a big one so far.
Good. Let's cross our fingers that's we're all waiting for that wonderful data, and also wondering if it will fit on our hard drive.
Oh, might be tough.
It might be tough, yeah. Anyway, I'm sure I forgot lots of stuff, but thank you for coming, and we're going to hear about cosmology with larger scale structure. And thank you so much for taking time, and you're on travel, and I understand it's hard to do that. But anyway, let's welcome Professor Jeltima.
Thank you. Yeah, and thank you for inviting me. And I should say, because I noticed that there are a number of people online, I am going to try to look at the chat and the raised hands and stuff. Do feel free to interrupt me with questions. I'm a little bit out of practice now from my remote teaching days of keeping track of all of the things at the same time. So yeah, let me, if I miss something, I apologize, and just interrupt and let me know. Good. Was there, I saw a hand in the room. Was there already a hand up?
That's just me moving around. Ignore me. All
right. Great. Fine. So yes, so today I want to talk a little bit about what we can do in terms of both you know, constraints on dark matter and the nature of dark matter, and also dark energy and the basic, you know, expansion history of our universe using the evolution of large scale structure. So just to start off, you know, brief overview of you know, what we think we know about the universe as of now. So, you know, this is a little diagram meant to show, you know, some of the major epochs in the evolution of the universe from the Big Bang until now. So, you know, we think the universe started extremely hot and dense and teeny in an event that we call the Big Bang about 13.8 billion years ago, and followed shortly by a period of very rapid expansion called inflation. Following that, the universe has been, you know, expanding and cooling over time. And, you know, initially the universe is what we call radiation dominated. In the beginning, it's extremely hot and it's just energy. And then as the universe expands and cools, we go through several phase transitions where first, you know, particles can form, and then they can bind into nuclei. And then at about 380,000 years after the Big Bang, electrons can bind into atoms. And this is the epoch of the cosmic microwave background. At that point, that radiation that's still left over from the Big Bang essentially free streams from then to us now. And that's the cosmic microwave background that's just, you know, a couple degrees, 2.7 some degrees Kelvin. And so that's our earliest picture of what structure looked like in the universe. And I'll come back to that. But really, all of the galaxies and stars and larger structures that we see started forming a couple 100 million years after the Big Bang, up until today, when we have a wealth of structure on all scales. So, you know, this is just a really simple pie chart of what we think the universe is made of. And, you know, with some twiddles here, we really only know the contents of about 5%. So that's in terms of energy density, 5% of the universe is in, particles in the standard model, things that we are made of and that we have been able to detect and characterize to date. Most of the mass in the universe is in the form of what we call dark matter. And most of the energy density currently is in the form of something we call dark energy. So I'll talk a little bit more about both of these. Dark matter at this point, we don't know what it is, but we know a lot about how it acts and what it can and can't be. Dark energy, what we really know is that at this point, the expansion of the universe is accelerating. So it's actually, the expansion is going faster and faster over time. And so there has to be something, gravity from the mass in the universe would slow that expansion down. So there has to be something else, and we call that dark energy. Okay, so this is just a little movie to set up, the evolution of structure over time. So this is a, simulation of a chunk of the universe in a box. And you can see that we're starting at very early times. The universe is almost exactly the same everywhere. So pretty much a uniform soup, not quite a uniform soup. And because it's not quite a uniform soup, as you evolve this movie forward, gravity pulls in mass into the denser regions. What started as very slightly denser regions become more and more overdense. Underdense regions become more and more underdense until you form what we call the cosmic web of structure, which includes, like here, every little dot in this movie, in this picture, would be like on the scale of a galaxy. And you can see that they clump into filaments and then larger structures, which I like to study, called clusters of galaxies. And then you get big voids, which aren't empty, but are a lot more devoid of structure than other regions of the universe. So as I said, so this is another simulation with a zoom in on one of the most overdense regions. So we get this cosmic web of structure on all scales, down to very small scales. At this point, we only have limits on like what are the smallest scale structures. But just an aside, if we could figure out what are the smallest scale dark matter structures that form, that can also tell us about what dark matter is. But what I like to study generally, not exclusively, but generally, are the most massive gravitationally bound objects in the universe, which are clusters of galaxies. So these form out of the very rare, very high overdense regions in the early universe, and they form at the intersections of filaments in the cosmic web. So a massive cluster of galaxies can have a mass that's like 10 to the 15 times the mass of our sun. And you might imagine that their formation is very sensitive to, for example, how much mass is in the universe, but also, that the expansion history of the universe, as these have to form in a universe that is actually expanding. Okay, so that growth of structure over time can tell us a lot about the nature of our universe. And so in particular, the growth of structure is obviously sensitive to that expansion history and the composition of the universe. And so, the game that we want to play here is looking at, our first snapshot of that structure is the cosmic microwave background around 380,000 years after the Big Bang. And then, more in the more recent universe, we have, huge galaxy surveys. So this is one projection of the Sloan Digital Sky Survey. What I'll talk about later is work we're doing in the Dark Energy Survey, which is goes even deeper than Sloan. But here, each point in this is an actual galaxy whose position, and then there's a redshift, a distance axis, has been cataloged. And you can quite clearly see what is shown in this movie borne out in the distribution of galaxies on large scales in the universe. And so, any cosmological model we have has to explain, that full history of structure formation. And in particular, the picture I have here is the picture of the cosmic microwave background that I'm sure you're used to seeing. But really, the cosmic microwave background looks like this. The cosmic microwave background is almost precisely the same in every direction. And those, what you see here are, if you can subtract off really precisely that uniform background, you can see that in fact it's not exactly uniform. There are regions that are very slightly underdense and regions that are very slightly overdense. But when I say very slightly, I really mean very slightly. The density contrast between those blue and red spots in that map that you are used to seeing at the cosmic microwave background, those only have a difference in density on the order of 10 to the minus 5. So the CMB is uniform to 1 part in 10 to the 5. And then from that epoch, so really those are very small differences. We start out with this very smooth universe. But that structure then has to evolve over the next, 13 billion years to give us what we see today, where, the things like clusters of galaxies and clusters of galaxies have overdensities of on the order of 1,000 thousands compared to, the background of the universe. So structure grows pretty rapidly, and that needs to be consistent with our cosmological model. And actually, this is one of, I could give a whole talk on the evidence for dark matter, and there are many, but one of the key points that, in my mind, well, also the fact that gravity waves travel at the speed of light to high precision. But one of the reasons why, at least I believe, we really need a dark matter that is like a new dark matter, like a new kind of particle, or maybe it's even little tiny black holes, but isn't just some modification of gravity. Because, you might argue okay, do we really need something new? Or maybe we just need to, the laws of gravity aren't exactly like GR. But, this fact that we can actually grow our structures, from the CMB to today, depends on the fact that you actually have dark matter there to seed that growth. If you had some modification, so the clustering of the normal matter is what you see, that is that the photon baryon fluid in the early universe that you see at the CMB. And if that was all there was, whatever modification gravity you made, if that was all there was, there's just not enough time for those densities, those small density perturbations to grow enough to form the structures we see today. And so you really need that dark matter there to seed those density perturbations and to pull things together in order to explain the history of structure formation that we see. Okay, so the history of structure formation, first of all, like I said, is one of the strong evidences that we need dark matter. But it also tells us how much dark matter there is in the universe. So, the fact that we form those clusters of galaxies, there has to be a certain amount of mass to make that happen. And so you can easily imagine that from that history of structure formation, we can get constraints on what is the matter density in the universe. But the history of structure formation and what structure looks like also tell us more about dark matter. So as I said, we don't know what the dark matter particle is, but there's a lot that we can learn about it from astrophysical observations. And those include that dark matter can't be relativistic in the early universe. So I say can't be too fast, but what we see is that structures form smaller structures first, clumping together to form bigger structures. This is called bottom-up structure formation. And that is a classic prediction of what's called cold dark matter, so non-relativistic dark matter, but the opposite of what you would expect if you had a very light relativistic dark matter species, for example, like the neutrino. And so, we know we want something cold-ish, but again, as in all of these things, we only have constraints. So one possibility is that it's not entirely cold. It's what we call warm dark matter. And that too has an effect on the way that structures look. It also can't be too light. How light it can be depends on if it's a fermion or a boson, but in general, there's a fundamental limitation on how light the dark matter particle can be, because we see structures on the scales of like very small dwarf galaxies. And so you can make a very simple calculation, which is, if I have something very light, it implies a fairly long wavelength for that particle, and you would effectively smear out structures on small scales. And so again, people will talk about what's so-called like light or fuzzy dark matter. But there are constraints based on like the smallest scale structures that we see on how light the dark matter can be. It also can't push on itself too much. So we know that, well, again, within limits, dark matter doesn't interact with us, with ordinary matter, except primarily through gravity. It's not electromagnetically charged. It doesn't have, strong force color. But that we don't know what the dark matter is, or if it's even one thing. So that isn't to say that there can't be, for example, new forces associated to the dark matter, where dark matter can interact with other dark matter. And so that's, broadly termed self-interacting dark matter. And again, we have limits on that, but it's an interesting possibility that, again, we can probe based on the way structure forms. Okay, so all of those things are constrained by some of the things I mentioned: bottom-up structure formation, the size of structure, substructures, and the shapes and densities of dark matter halos. But again, we only have limits on these, and there are tensions, particularly on the smallest scales. So there are also potential astrophysical explanations for these, but the population of dwarf galaxies in the Milky Way, the densities in the center of those dwarf galaxies, are they cuspy or chord? What turns out to be hard to explain in a simple cold dark matter is just the diversity of types of galaxies that we see. And so there are hints that or at least places that allow for dark matter to not just be a purely cold, collisionless particle of some kind. And so, all of these things here are things we can test by looking in more detail at structure formation. So on this, I'm just going to tell you about like a couple of recent or ongoing projects that we've been working on in my research group, and then I'm going to transition over to cosmology. So in particular, recently we've been interested in this question of does dark matter interact with itself? And if it does, there's a number of observational consequences that we can test, and then place limits, or maybe actually see indications of this possibility. And so here we consider this just very generically. there are a variety of like particle models that can give you some kind of interaction. And generically, there's a few observational consequences that you expect. So the first is that if you look at the density profile, so from, you take any actually dark matter halo, a galaxy, dwarf galaxy, cluster of galaxy, and you look at how the density, these objects will get denser and denser towards the center. But in a purely collisionless, non-interacting dark matter, you would predict that, the density gets denser and denser, up to like very high densities in the centers of dark matter halos. If instead dark matter has some kind of self-interaction, you expect a plateau, so what we call like a chord dark matter profile, because those particles now can push and scatter each other, and so you wash out. You can't sink all the way to the center, and you get a fairly constant density in the center, and that's something that we can look for. And it's, there's indications, for example, on dwarf galaxy scales of cores in some dwarf galaxies, which is one of those like tensions with cold dark matter that people like to argue about. Another observational consequence is that your dark matter halos look rounder and less elliptical, again, because of the scattering of dark matter particles with themselves. And so those are examples of things that we can actually then go out and look for. And so we've had a couple recent projects and some ongoing work in my group. I'm just going to very briefly summarize. So, the first was a former graduate student that graduated was working on this question of, are galaxies, elliptical? Like, are they more elliptical or rounder? So that prediction of the shapes of galaxies that would, potentially indicate some kind of self-interaction. So what we found in brief, so Alex McDaniel, he looked at a bunch of nearby elliptical galaxies and found that, what we found is consistent with cold dark matter. We can't rule it out, but in fact, they are a bit rounder. So here, the lines are our fits to various subsets of our data. Green is simulations, expectations for cold dark matter, and then some amount of self-interaction and more self-interaction. And so we can't rule out the cold dark matter, but we also find something that's consistent with some mild amount of self-interaction. Similarly, there's the paper that's actually was just out on the archive a few months back. This was actually led by 2 undergraduate students in my group. And so one of the things that we looked for is that, sorry, there's a little bit of an echo. I don't know why. So in clusters of galaxies, there's typically a galaxy near the center of the cluster. And one actually turns out to be a fairly robust signature from simulations of that, chord density in the center. So if, clusters have more of the, constant central density versus something that like is, really dense right at the center, what happens is the galaxies in a galaxy cluster orbit within the cluster. And if that central density is flatter, then the galaxies near the center are able to orbit basically out to, they're less constrained to the center. They can orbit out to larger radii. And so generically what you predict then is that, those galaxies are offset from the dark matter center of the clusters. And so, these 2 students looked at this again in a number of clusters, and what's shown here is the offset distribution. And what we found, again, similar to the elliptical galaxy case, is that what we find is consistent with cold dark matter. I mean, in both cases, we need larger sample sizes, but we did find a non-zero offset that is on a scale that would be also consistent with some kind of mild self-interaction. So those are a couple of examples. Something that I have a graduate student working on now, I don't have results to show yet, but what we've gotten excited about now is using strong gravitational lensing of clusters of galaxies. So this is a beautiful one that was found in actually the dark energy survey in one of our samples. So what we're looking at then is the bending of the light of background galaxies by the cluster in these giant arcs in strong gravitational lensing is very sensitive to the enclosed mass. And so in these strong lensing clusters, you can much more precisely constrain what is that central density, and does it look chord or does it look cuspy? And so we have a sample of about 20 clusters drawn from the dark energy survey and elsewhere that we're going to be using to look at this. Okay, so I now want to transition over to dark energy and cosmology. Are there any questions so far? I just want to pause.
Let me just say, you sound and look great on this end. So any echo is, we apologize.
Okay.
We apologize for it.
I think it's just the room occasionally picks up some sound.
Okay. Okay. Well, then I will just plow ahead and not worry about it. Okay. So as I said, compared to dark matter, we know relatively little about what we call dark energy. What we know is that the expansion of the universe is accelerating. And so what is the cause of this cosmic acceleration? Here, it can be some new component of the universe called dark energy. So a new effective force that is pushing out and driving that accelerated expansion. It is possible, I think on the dark energy side, people still talk about modifications to gravity that can explain this as well. Luckily, the difference between those two is, again, testable with the surveys that we're conducting. And if it is dark energy, so far everything we found is consistent with a cosmological constant. So, the vacuum of space has some energy, very, very small energy density associated to it, and that is constant over time. Versus, a lot of forces you might imagine can evolve as the universe evolves. So, one of the fundamental things that we want to test is, like, so far everything's consistent with a cosmological constant, but we frankly don't have super strong constraints on the evolution. We have pretty good constraints on the current energy density in dark energy, but how it evolves, not so much. So that's really something that is fundamental to the nature of dark energy that we would like to understand. Okay, so that, again, like dark matter, structure formation is very sensitive to the expansion history of the universe. Up until the very recent past, the universe was so-called dark matter dominated. So, if there was no dark energy and it was just, the expansion of the expansion of the universe set up by the Big Bang, and the mass in the universe and gravity pulling in, then you would expect that the expansion rate would slow down over time. And for most of cosmic history, that is in fact what happened. But what happens is, so if dark energy, whatever dark energy is, its energy density is extraordinarily small. And so in the past, the effects of dark energy were negligible compared to the gravitational effects of the mass in the universe, back when the universe was much smaller. But as the universe expands, the mass gets more dilute. If we're talking about something like a cosmological constant, more space means more dark energy. And so, this is exemplified by, this little graphic that I really like, the cosmic tug of war, that, at first, the weight of the dark matter of mass in the universe is winning. But, as the universe expands, we put in more dark energy balloons, and, actually relatively recent recently in the past, and you can make a little calculation, we transitioned to the epoch of dark energy dominating and that expansion accelerating. So actually it's pretty cool, because if we lived in even a slightly different place in cosmic time, we might not know that dark energy was there at all. And this was just a tweet from a former graduate student who realized that, in fact, actually, if you think about like at what time the universe became dark transition to dark energy domination over over mass domination, it's about the same time as the first life appeared on Earth. So this really truly is fairly recently in cosmic history. Okay, so obviously what we see is that the expansion appears to be accelerating. So what can we look at to learn more? Like, how can we learn more about dark energy, how much there is, and whether it's evolving over time? So our probes generally fall into kind of two general categories: geometric probes that allow you to measure cosmic distances. So type 1a supernova, which are so-called standard candles, fall into that camp. And then there's probes like weak lensing, clusters of galaxies, things that allow you to measure the evolution of structure, so the growth rate of structure over time. And in fact, actually, surveys like the Dark Energy Survey and LSST with the Rubin Observatory upcoming do multiple probes in one survey, and so have both types in a single survey. And that's great because the combination can allow you to disentangle the effects of dark energy and modified gravity. So here, these are just some examples of in a universe that has more dark energy, you actually start forming structures earlier to be able to form we see the structure we see today. It had to get there somehow. If there's more dark energy, then we transition to dark energy domination earlier, which effectively shuts down structure formation because things are now flying apart too quickly to gravitationally collapse. And so in maybe a little bit oddly, in a universe that has more dark energy, you expect to see more structure as you look in the past. And then obviously distances, more dark energy means that, again, that acceleration starts earlier and things are farther apart than they would be otherwise. Okay, so we have a model, lambda CDM. So this is cold dark matter with a cosmological constant that fits our observations overall extremely well. I noted that cold dark matter isn't perfect, maybe at like dwarf galaxy scales. But in general, if you take our lambda CDM models and you apply it, it fits well the cosmic microwave background, and then you say, okay, let me, given that model, evolve it forward, and it fits pretty well the structure we see today as well. We do have two kind of interesting tensions at the moment. One a little more interesting than the other, just in terms of significance. But one of those, so the first of those is a tension in the Hubble constant. So the Hubble constant is that measure, it's a measurement of the scale of the universe at different epochs. And so if you look at, say, measurements of the Hubble constant from, at early time, so using the cosmic microwave background to measure the Hubble constant, compared to measurements of the Hubble constant at late time, so in our cosmological surveys, also from lensing time delays and actually a myriad of different types of measurements, these get different results that are actually starting to be pretty significant. And so, we're still have to, nail down that there aren't any systematics in our measurements of distances in the local universe. But, this is actually a quite interesting potential tension in the lambda CDM model is that, we don't get consistent Hubble constants at early and late times. And so, there's various ways to try to solve that, some like things called early dark energy, but it would imply, some modification potentially of our standard lambda CDM model. The other one is more closely tied to structure formation, and it has to do with a parameter that measures, is sensitive to the growth of structure called S8. So what this is a combination of, if you want to predict like how much structure you have in the present universe, it depends on obviously the matter density. It also depends on the amplitude of those early density perturbations. How big did they start out? And so S8 is a combination of those. And again, interestingly, at a, it's interesting, but it's not significant enough that I think astronomers are writing home about. But what we do see is that, again, looking at this parameter based on cosmic microwave background, we get a 2-ish sigma difference from what we would measure from, more recent like galaxy survey growth of structure probes. So right now, again, let's get more data and work harder and make sure that it's significant. But we don't, the growth of, if you take your predictions from the CMB and your lambda CDM and then evolve them forward, we're not quite getting the structure we think we should see. So that's another interesting potential tension. Okay, so how can we learn more? So one of the projects that I've been very involved in over the last, 10 years now is the Dark Energy Survey. So the Dark Energy Survey was a 6-year survey. We're finished taking data, although we're still working on, we've got results from the first 3 of those 6 years, and we're working on the final results now. But it was a 6-year survey that covered about 1/8 of the full sky using the Blanco telescope in Chile, and cataloged over 300 million galaxies in its survey lifetime. In addition, we have several fields that were observed more frequently, like every few nights, to look for things like supernova. So we can do supernova cosmology as well as growth of structure cosmology in the same survey. Okay, so I think I need to speed up a little bit. So I'll say this is a picture from one of our collaboration meetings. It's a large collaboration of over 500 people around the world. This is just as an observer, I want to impress on people that just might download the galaxy catalogs, how hard it is to actually make those very precise measurements of 300 million galaxies. So this is a raw image from our camera. You can see it's a mosaic of not quite 70 CCDs. And you see how ugly it looks. There's a satellite trail. There's differences in the sensitivity. And then, you run that through the data reduction pipelines, you clean everything up, and you get gorgeous images like this one. So this was one of the last images that was taken in year 6, and there's a massive cluster of galaxies here. Okay, so in terms of dark energy probes, as I said, there's those that are sensitive to the growth of structure and those that are sensitive to the geometry, to the expansion. And in the Dark Energy Survey, we do a combination of these. So there's supernova, and baryon acoustic oscillations are like the imprints of those same cosmic microwave background perturbations, but in the distribution of galaxies. So those are geometric probes. And then we have things like galaxy clusters and lensing cosmic shear that are sensitive to the growth of structure. So we do all of these in a single survey. And just because I don't like empty quadrants, I also want to note that we do tons of other non-cosmological science in the Dark Energy Survey. we found a number of new trans-Neptunian objects. We observed the optical imprint of the first neutron-neutron star gravity wave event, Milky Way structure and local dwarf galaxies. So there's a lot that you can do with deep data on an eighth of the sky. Okay, so in terms of like, how do we then constrain cosmology? We have a number of ways of doing that. So first, you can look at the distribution of galaxies, right? So one metric is just what's called the 2-point correlation function of galaxies. It's like if I take a galaxy and I measure the distances to other galaxies, and I do that for all of the pairs of galaxies I have, then I will get, based on structure formation, peaks at certain scales, right? I'll have a higher probability of finding another galaxy at certain size scales. And this is a measure of the clumpiness of the universe. And with the limitation that what we really want to know is the distribution of the mass, which is mostly the dark matter, and the galaxies are tracers, but not perfect tracers of where the mass is. We can also look at the cumulative effect of lensing. So, if we have the galaxies that are farther away in our survey, those pass through all of the possible structure along the line of sight to us, and therefore their light gets lensed, so their magnitudes change, their shapes change, and in fact, if you look at this is a function of pairs of galaxies. If you look at the correlation in the shapes and alignment of a pair of galaxies, because two galaxies will nearby will be affected by a lot of that same structure, there's a correlation in the ellipticities in their alignments that we can measure, and that is a measure of the structure along that line of sight. So here we're looking at statistics of the correlation in the shapes of pairs of galaxies. And just for fun, this is the DES field of view. It kind of looks like a steamboat, or maybe the Starship Enterprise, depending on how you squint at it. But this is just, showing that if you take that lensing and you map the mass over our field of view, this is a map of the mass distribution within the survey, which is pretty cool. Okay, so some of our basic cosmological results come from what we call the 3x2 point analysis, and this is a set of 3 2-point statistics. So one of those is the galaxy-galaxy clustering that I mentioned, and one of those is the shear, the correlation in the shapes. But there's also the correlation between the galaxies and the shears. And if you put those all together, what's really nice is that this combination of probes allows you to essentially calibrate away systematics in your measurements, like that galaxy bias or the uncertainties in the redshifts of my sheared galaxies. So the combination is quite powerful because it allows us to jointly constrain cosmology, which we want, and astrophysical and systematic parameters. So as I said, what I work on mostly is clusters of galaxies, and I've already mentioned this. So these are the most massive gravitationally bound objects in the universe, and they're quite rare. And so they, how many clusters, if you sample some volume, how many clusters you see is highly sensitive to how much mass is in the universe, but also that expansion history, right? How long did these have to clump together before they were flying apart flying apart is not the right phrasing for that, but expanding away from each other too quickly. And so, so in fact, actually, clusters have been key to cosmology for a long time, starting with Fritz Zwicky. Observations of the Como cluster was the very first evidence for dark matter, and clusters gave the first strong constraints on the matter density, indicating that, in fact, the matter density is less than 1, like that we didn't live in a critical density universe in terms of the mass. And so now we're using these again to get more detail on the dark energy density and its evolution. And in the interest of time, I'll go a little bit quickly, but I did want to say that the trouble here. So what we can predict in theory is like how many dark matter halos of a given mass in some volume at some epoch in cosmic history. What we see in the dark energy survey, which is, it's a 4-color, you get some color, but it's an imaging survey. What we see is distribution of galaxies. And so we can try to find clusters based on places in the universe where there's more galaxies, and in fact, more galaxies of the same color. And then, so the hard part is then, taking what we can see and relating it to, what we can predict, which is the mass distribution. And so a lot of what my group does, in fact, is a lot of like follow-up observations to understand the selection of clusters in our survey such that we can do cosmology. And as I'm running short of time, I probably won't get to all of the different projects we're working on, but this is just to note that one of the hard parts is the projection of galaxies along the line of sight. So, if we find a cluster because there's a lot of galaxies, and, to a reasonable extent, the number of galaxies in the cluster correlates with its mass. So it allows us to predict its mass. But we can't precisely decide which galaxies are in the cluster versus behind or in front of the cluster. And in fact, our selection can be biased if there's another cluster or a smaller cluster along that same line of sight. So we have a biased selection. And so a lot of the work that we do is to understand and calibrate all of those effects. And this is just saying that, that bias in selection also biases our mass determination. So we're preferentially selecting things that have structure along the line of sight. And so that's something that we're working very hard on understanding so that we can get out the cosmology results we want. Okay, so this is just a slide to show you how hard this is. This is the cluster cosmology and integrals. And these are some of the systematic effects that we have to calibrate for. But I think I'll stop here and I won't go into then the details of how we do some of that calibration. And I'll just leave you here with some of the cosmology results now. So here, and this is just boiling down like 40, 50 papers into 2 plots. So, putting together all of this is just from the first year of DES, actually, that 3x2 point analysis, adding in clusters and the clustering of clusters, we get the red contours in terms of the amplitude of density perturbations and the mass density. And you can compare this to Planck in green. So just the first year of DES was nearly as sensitive as Planck. And you see this offset that I talked about in terms of that S8, that growth of structure parameter. And then this is, similar results from our year 3 analysis just now for the 3x2 point. The tension's gotten a little bit less, but it's still there. So, putting everything together, you can see like the precision of the constraints that we're getting out of DES. In fact, okay, so you can see this parameter W, if it's exactly -1, that's a cosmological constant. And you can see that we're getting much more precision on this. And in fact, so far, everything is consistent with cosmological constant. And, we also have precise constraints on the matter density and the sum of neutrino masses coming out of this. And so I'm going to leave you with that. Sorry, I'm going to skip through quickly. And I will just, leave you with this, which is the Rubin Observatory and the Legacy Survey of Space and Time that it will be conducting. So this is is our beautiful camera that I actually got to see in the clean room at Slack at our recent collaboration meeting. It is the world's largest camera with 3.2 billion pixels that will be shipped, in the next, I think now we're talking about March, down to Chile to our custom designed dome. And, Dark Energy Survey in 6 years covered 1/8 of the full sky. The Rubin Observatory is going to cover half of the sky every 3 to 4 days for 10 years. So this is going to be just extraordinary for a lot of science, including dark energy, but also, anything optical transients. You're going to have half the full sky every few days. And it's just going to be amazing. So I'll stop here.
Hey, thanks so much. I have a comment for the students, because there was an image of Fritz Zwicky, and I wanted to assure the students, lest you think that image was prejudicial in some way. No, it's exactly an accurate depiction of Fritz Zwicky.
It's just pictures of, I can't resist sneaking that into talks, because pictures of Zwicky are just so fun.
That's fantastic. Any questions? You have a question?
How do we thanks for the talk. How do we distinguish between the lambda CDM model and the dark energy from the experiments? Like how would we determine that? Like it's not the geometry of general relativity, but some unknown entity like a dark energy.
Right. So essentially, if you have both probes of the geometry and the growth of structure, you can distinguish by putting those together. So you can have a modified gravity model and a dark energy model, which produce the same geometry, but they won't produce the same history of the growth of structure. So that is, so it needs a combination of probes, but it is something that we can do. And then I saw there's a comment in a question in the chat that's, what is the plan to remove satellite scratches? So if it's a single satellite trail, it's fine. I mean, we have multiple images of the same patches of sky, and there's algorithms where you can go through and flag and remove things. Unfortunately, when you have constellations of satellites, that's going to become pretty problematic. So Starlink is not so good for us, I will say.
You said that very politically. Yes, Chris.
Yeah, thanks for the talk. So it's always been my understanding that that clustering relies so heavily on the accuracy of the redshift measurements. But you were talking about that with this 3x2 point function, you might be able to kind of bypass that. I was curious in terms of LSST, which will be mostly, photometric redshifts, how that would affect what you're doing, or if you're not worried about it because you have, these super secret techniques.
No. If I was going to list something that keeps me up at night in terms of how well we can do, it's definitely the accuracy of the photometric redshifts. In practice, what you do is, it's all treated very probabilistically. So you have it's not like you assign a redshift to a galaxy. You have a distribution of it's a P of Z, a probability of that redshift. And so, we try to then, fully fold that in and marginalize over that in all of the cosmological constraints that you see. How well we can actually measure that probability distribution of redshift is, one of the fundamental things that we work really hard on. And so, right. So LSST is also going to be a photometric like the dark energy survey. It will be, it will do somewhat, it will do better. It just depends on the well you can measure your magnet, the colors of the objects, and what you have available in terms of redshift surveys to calibrate with. So, I mean, it's a huge effort. We are trying to do our best job, and then ultimately, as well, I mean, that is one of the factors that, creates the size of the curves that we can determine. So I can say LSST will do better at photometric redshifts than DES, but it's definitely something that we work really hard on. If somebody wants to build me a spectrometer in the South that I can dedicate to LSST follow-up and calibration, that would be great.
Fund me and I will do it. Sounds like a great project. I have a leading question. Maybe it'll be our last question. So before recombination by 1,000 years or whatever, so the situation then was we had free electrons and photons, and they were interacting all the time. You had electron scatterings. Basically, the radiation field was in equilibrium with the matter at that point. And I think if you just left it to the baryons, and correct me if I'm wrong, the radiation plus the baryons would be trying to erase all of the any density perturbations that there might have been from early quantum fluctuations. So yeah, I mean, you can interrupt me. So you really need.
You'd get oscillations like the CMB, even if you just had the baryons. I mean, it's kind of like a harmonic oscillator. Gravity pulls in. I mean, it's still gravitational, and then the plasma pressure pushes out, and so it really is. I mean, what you're seeing is, I mean, it's acoustic oscillations of this plasma fluid. So those would be there. It's just that they couldn't, they start out with such low density contrast, they just can't grow quickly enough.
Okay, yeah, but dark matter could have clumped up much earlier.
Yes, yeah, because dark matter to a certain extent gets drug around by the baryons because of gravity, but because it doesn't, I mean, okay, if it had really strong interaction, like some strongly self-interacting dark matter, maybe, but right, it's free to sink at that point.
Okay. Thank you.
Yes, sir. Coming from Sudan.
And sequence.
Oh, yeah. So the back to the photometric redshift discussion. Yeah, is it basically the same kind of idea from Newman 2008 that you're applying, or is there something newer than that?
There are there's a number of methods, and actually the methods have changed over time. So if you want to email me, I'll send you some papers. And that's probably the best, because it's also not exactly my field, but yeah, there's a lot of things. There's various different algorithms for trying to determine the photoz's. We use some of the correlation functions to help anchor the photoz's. There's this whole self-organized map method of it. Yeah. So, but I'm happy to send some references.
That will be great. Thank you. I'll follow up.
Okay.
Thank you so much for coming, and thank you again.